Sorry?
We have got up to 12.
We've got up to 12, but I'll start with number 1. Sorry. So, I'll quickly summarize those points. So, the first point had to do with the definition of random event, and I won't go back into discussing it very much, but we all had the notion of a random event as something whose occurrence we cannot guarantee, but we can say something about the probability of it happening, and part of our aim is to be able to calculate the probabilities of certain random events which are of some interest. Then we had the probability of occurrence of a random event, and if we had mutually exclusive events labeled by some I, then we had the summation of pi equal to 1 if they exhausted all possibilities. Then we went into some examples of an unfair coin and a fair die, and we examined those. Then we came to the idea of probability distribution. And by probability distribution, I meant what the mathematicians call probability density, not the cumulative distribution, but the probability of something happening or some event actually taking place. And we, in the two examples that we had pictures of this sort. For the options for a person to take steps of length 1, 2 or 3 with equal likelihood, left and right, or with the unfair coin we had this sort of distribution for heads or for tails. Of course, I am exaggerating the difference between the two. Here we had some 0.51 and 0.49 or whatever, it does not matter, but these were examples of probability distributions. These were of course distributions for discrete variables. At that point we actually went ahead and we also noted that given a probability distribution, we can calculate many things based on it. For instance, the average value of some observable would be the sum over n, p of n times n. Likewise, probability of n to some power, let me call it let me not write it like that, n squared would be the sum over n, p n, n squared, etc., etc. This was called mu, which is the average value of n. We just specially called it mu, and then we also defined the variance sigma squared, which was n squared minus n average squared, which was the same, identically equal to n minus n average the whole squared, and it tells us about the width of the distribution. So, this is the mean, this is the width, or the width squared of the distribution. So, this is the first 3 or 4 points that we had. Then we turned to number 4, which was the probability distribution for a continuous variable, for a continuously varying variable. Okay, and that we said, for instance, if we had something like that, we said we have a probability density p of x. We are using the same notation p of n and p of x. They mean slightly different things. P of n is actually the probability p of 1 here is the probability of getting 1 as an outcome. P of x here is the probability density. So, P of x times dx. So, P x dx is the probability of the outcome or the being in the range x to x plus dx. All right. And then we talked about various ways to characterize this distribution. One was simply the average value. Then we had variance, which was sigma squared. So, we could write it as x minus mu the whole squared px. The mode most probable, median. Okay, I won't rewrite the definitions as much on the left as on the right. Then we give examples of so this was point number 5, and point number 6 had to do with particular distributions, in particular the normal distribution, where the width is characterized by sigma and the form is 1 over root 2 pi sigma squared e to the minus, in general, x minus mu the whole squared over 2 sigma squared. Although here we have drawn it for mu equal to 0. And just as another random example, I just told you about the exponential distribution e to the minus lambda x. Lambda times this is the normalized distribution. And although it decays quite rapidly, it is not as rapid as the Gaussian. Okay. Right. Number 7. For instance, even for coin tossing, the distribution near the center has a Gaussian form, but if you examine the very tails, they decay exponentially near the edge, I mean. Okay. So, then we asked for combining random variables. For instance, the favorite and important case is adding a lot of variables to get some variable capital X of n. And the question is, how does x n scale with n? What is the distribution of the scaled variable? So, for instance, if we have let us say x is drawn from a probability distribution of the finite value of mu, the proper scaling of x n would be, so we will define a new variable which we might call y equal to x n over n. This is one way, this is the first thing we might do. Okay. And we can ask for how the distribution of y converges, how does y converge to the value of mu? I mean, this is one question we could ask. Okay. And of course, y, I mean, so that is one. The other one would be, other than converging to the mean value, what is the width of the distribution? How does it scale with n in the limit of large n? So, most conveniently, let us assume mu equal to 0, and in which case, in some sense, we are defining the variable x n Okay, so in the case mu equals 0, alternatively you can shift out, you just define shifted x's so that you have this variable x1 plus x2. This is in the case mu not equal to 0. On the other hand, suppose I have shifted out the mean and I have these variables x1 and up to xn, then the correct scaling of xn is actually with the square root of n. And this variable y, in terms of the variable y as put here, we have a Gaussian distribution. So, e to the minus half y squared, if we put in sigma squared here as well, is the way the distribution will scale, other than 1 over root 2 pi y. Okay. I hope there is no confusion between this step and that. Here I am just saying that if there is a mean value mu, then y will approach mu in the limit n going to infinity, and this is the way. So, maybe I should not use the same letter x. In other words, so let me, if you like, we could define these as x hats, where x I hat is the original x I minus mu, okay, with respect to the mean, the shift from the mean. And you ask, how do these shifts, how are they distributed? The answer is that they are distributed in this way through a Gaussian. Okay. All right. So, actually, I see I have jumped, I have included part of 8. 8 was on how to combine, how to write joint probabilities. And this was an important point. We said that P n of, if you wanted the probability that, okay, so with the same definition. So, let me redefine again, just in case it is not clear. X equal to x1 plus x2 plus xn, and we said to find the probability distribution of x, we called a capital P of x. We need to sum over all options if it is discrete of x1, x2, up to xn with the corresponding weight for x1 to occur, x2 to occur, xn to occur, times a Kronecker delta of capital X, comma, summation xi. Okay, let us just examine this equation again. We want the probability for the occurrence of a given value of capital X. Capital X is a random variable because it is made up of a sum of random variables x1. The probability of occurrence of each random variable we are assuming right now is independent of the other. Therefore, the probability of occurrence of x1 comma x2 comma xn is the product of px1 times px2 up to pxn, because it is independent. This sum over all options with the correct weightage of the probability for that option to occur is good, but we want to capture those events which we really want, and those are the events in which the summation of xi is actually equal to our desired value x, and this is the way we can do it. Does this make sense? Okay. And of course, then we wrote the generalization of this in the case that this is a continuous variable, discrete, continuous, and we said that this is the integral over dx1 through dxn, px1 through pxn, delta function of capital X minus summation xi. So this was what we had. One important point, this sort of equation, of course, the way it's written has assumed that x1, x2, x3 each is independent of the other. Suppose they had not been independent. In other words, if you knew that the first time you get x1, the probability of getting a certain value x2 is influenced by that choice x1, and so on and so forth for x3. Well, could we have written something similar? The answer is yes, we could, except that we have to, in the general case, most general case, p of x would be similar sum over x1, x2 up to xn times the probability, and this time we will have no way of separating it out, of x1, x2 up to xn multiplied by the delta, let us say Kronecker delta or the delta function of capital X and x1 plus x2 plus xn. This would still be true because you are taking an event which is a compound event, meaning you have x1 and x2 and x3 and x4 all together. There is a certain probability for that. Let that be prob this, and then this. What is a familiar example of a correlated, correlated, I mean, where the probabilities will not factorize? Answer, the Boltzmann weight. I am preempting what Shamik will tell you, but you all perhaps have heard that in the canonical ensemble, the weight of a given configuration is given by the energy, and the energy, for instance, if we are referring to molecules or something, the configurational part of the energy will depend on the locations of the molecules. So, this, for example, could have been e raised to this prob e to the minus beta times energy, which depends on the locations R1, R2, of course, generalizing to 3 dimensions, Rn. Okay. And there is no way you can factorize this, because you have potential energy which depends 1 and 2 on 2 and 3, and 3 depends also interacts with 5 and 4. So there is a whole lot of energies here, pairwise energies, but even if you have pairwise energies, the whole sum there cannot be factorized into prob this way. Nevertheless, you can write this, of course, this is not quite right, divided by the partition function which I will denote by q. So, this is the probability of occurrence of configuration. It would just feed in. So, for instance, suppose you asked the question, where is the center of mass? Okay, center of mass is not a very good, well, it is okay. Suppose you asked where is the center of mass of 3 molecules, particular molecules likely to be x1. Well, choose those configurations in which those 3 molecules have a center of mass at capital X. Choose those events. This would be valid. So, this is a very general way of doing things. Indicator function is what we called it. So, in general, actually we wrote yesterday in number 9 that what did we want? We wanted the probability of a certain event and we said that we can write it as the sum over all possible configurations. Like in the Boltzmann case, you would have to sum over all possible locations of R1, R2, R3. Those are all possible configurations. Probability of that configuration times an indicator function which also depends on that configuration, divided, well, not divided, that is it. No, this is okay, where eta of c is 1 if the event occurs and it's 0 otherwise. For instance, eta of c could have been the event that in a spin system you have spins, let us say ups and downs, arrange the spin. Here is a certain site I and here is a certain site j, different from I. You could ask for the event that at both I and j the spins must be parallel. Okay, in this picture they are, but as I change configurations they won't always be parallel. It's an event. So what will I get if I put in some object eta of c, which is 1 when they are parallel and 0 otherwise? I will pick out the probability, it is a joint probability that the two spins will be parallel. Okay. So this is the way to do it. We'll come back to this in a little more detail in a little while. Then we applied all these things to the random walk, and we just recalled that the event is that the event of interest may be that after n steps walker is at site M. And then we said that if there are n steps, the probability of any history of those n steps, left, left, right, right, etc., is 1 over 2 to the n, because there are 2 to the n options for the histories, and each is equally likely. So this is 1 over 2 to the n. Okay, so we had a sum over all histories, 1 over 2 to the n, eta that after n steps the walker is at site M. So you had an indicator function of this sort. This was then easy to go ahead and calculate, and we found that this is 1 over 2 to the n. We included all the cases that contributed, and this turned out to be n factorial divided by n r factorial, n minus n r factorial. Okay. And then we carried on with the analysis after that. Okay. That was point number 10. So we are still, yes. Yes. Summation n p n, you should divide by summation n p of n, but that summation n p of n is 1. You should not divide by summation n, you should divide by summation of n p of n. You should do, in other words, you are summing over all options with the appropriate probabilities, but that is 1. So that is why I am not dividing. Which one? This? Don't they look alike? Yeah, they look alike. You want to interpret something in terms of something else? I mean, they look alike, but they are actually different, I think. Okay. Yeah. You are right. So this is the mean of something. Here this was the mean of n. Okay. So perhaps as the most general statement, we should say that the average value of anything, A for anything, is sum over all possibilities. Let us say C, prob C times A of C. This is always true. Here we wanted the average of n. So that is what we put in and we got this. Here, as Weber correctly points out, we are getting the average value of the indicator function. So, probability of an event is the same as the average value of the appropriate indicator function. When you say it in that form, it is perhaps not totally obvious, but this simply writing it out shows that it is, because the probability of eta has to be this, but then eta has the property that it rejects everything that is not to be counted. So, that gives you the probability of that event. Is this all right? But good point, you notice this similarity. It is actually there, but the meaning of eta further comes in. Good. 11. So, when n is large, we get approximations to the function, and P n of m, which we sometimes denoted initially by P m n, is about 2 over root 2 pi n e to the minus half m squared by n. So, let us hark back to the first lecture, where we had the random walk, displacement m, and there was a question yesterday that if n is going to infinity, we are also using m large somewhere, but then we are saying m by n is 0. That everything is true there, because in the random walk, just as an aside, let me just say n is large, m is large, but typically of order root n, not always, but typically of order root n. So, when n goes to infinity, m also goes to infinity, but the ratio m by n is of order 1 over root n, and that goes to 0. So, there is no contradiction, because we actually use the smallness of m by n in order to make some Taylor expansion in something. So, we are allowed to do that after realizing that both m and n are very large. Yes. Was there a question? No. Okay. Okay. I thought. Sorry. Okay. And then we took a continuum limit. As I said, you can do it in two ways, and both ways give you the same answer. And the answer, so I won't go over the ways, is that you can rewrite the profile in the form, okay, I don't, but okay, we have often written it in the past, 4 pi dt e raised to minus x squared over 4 pi, no pi, no 4 dt. Okay, so this is in the continuum limit. So, this brought in the feature of the diffusion constant, and I do not know what else. That was it. 13. So, this is, was this 12? This is where we had reached? Okay, good. So, we will carry on with a few more, 4 or 5 more. Okay, so actually this is a point that somehow I think I discussed yesterday, because of, one goes back and forth. The 13th point was simply the following, that yes, we realize that this is the form that we get from a particular problem, but then this form is seen all over the place. It seems to be more universal than just the random walk. So, is it actually is it possible that the final answer transcends the exact model that it arises from? Okay, so let us perhaps discuss quickly the first homework problem in this context. The first homework problem had to do with the random walk. I mean, this is as an aside, or maybe I should do this discussion right in the end. So, there is a walker which can go left or right with probability 1/3. On the other hand, it can just stay there with the probability 1/3. And the question is, what is the long time behavior of P(mn) in that case. Okay. We will come back to that. I think let us leave the discussion till we finish all the general points. I know some of you have attempted the problem, but I don't know about all of you, but we will quickly indicate something about it as we go on. So, 13 is only the question, is this form more general than just for the random walk that we dealt with? Okay, that was a question. Okay, so 14 is the answer. The answer is yes. I'm sorry to stretch this out so much. What did I do? Oh. What was the joint probability of this happening together? Was there a causal connection? Well, yeah.
We have to go to many histories.
Yeah, to see this. Luckily for you, to happen in the first history. Right. No, I really thought I caused it. And maybe, you never know. I mean, somehow molecules here and there. No. 14. You know, there was this big blackout once in New York City. I mean, of course, there are blackouts everywhere, but this was since it happened really. But I remember that there was this blackout, and you know, we in India were reading about it and saying, oh, big deal. But for them, it was a very big deal. And apparently, just before the blackout happened, there was a housewife who couldn't get her iron or something to work. So she jabbed the plug into the point, and that moment the whole city went black. And she said, good God, what have I done? You know. Likewise. Yeah. Right. Okay. Now 14. This form, namely, this is the form we are talking about, is the asymptotic, describes asymptotically the displacement for any, I am talking now and then in terms of random walks, but you could imagine any variable p of x requiring only so long as the sigma squared is well defined, which of course not presupposes, but which implies that mu must have been finite, it must be that the asymptotic form is described by x squared over 4 dt. Okay. In that case, of course, the diffusion constant is given by half r times sigma squared times dimensionally. All right, let's say that x is indeed a length here. So this is sigma squared carries the units of length, or just to be in conformity with our earlier notation, let's put in the a squared here, a being the step length. In fact, if you like, in the case that we had a biased random walk where we had a drift velocity, this form generalized to e to the 1 over 4 pi dt e to the minus x minus ct squared over 4 dt, and this all holds with c equal to half well, r times average value of x, which would be r in my notation, r times mu times a. All right. So, this is a very powerful statement. It says no matter what you start with, you can find the, your primitive distribution is given, find the mean, find the sigma squared. It's a finite calculation. You can do it in about 10 minutes maybe. Having done it, go ahead and make a prediction, and this is the prediction. It's a strong prediction that the distribution of x at large time will actually be governed by this distribution. Of course, there are two parameters in the distribution, d and c, but they are known in terms of the microscopic parameters of the probability distribution, and the only thing that matters in your initial probability distribution is sigma and mu. So, it's an immensely strong and useful, practically useful statement. So, I hope this statement is clear. Okay. Okay, so having written this, maybe we go to that homework problem and then come back. Of course, I won't solve the homework problem, I am sorry. That, you have to do the binomial, you have to generalize to multinomial to nr number of right steps, nl number of left steps, and n0 number of weighting. So, that squared, so the factorial, n factorial divided by the product of the 3 factorial, you have to work that out, the asymptotics. But armed with the result that we have here, we can work out the answer in one shot. Why? Because, okay, so let us see, this was the situation at hand. So, there is a walker, probability 1 by 3, right, 1 by 3 left and 1 by 3 does not move. Okay. Is the statement of the problem clear? That too will obey and have something of this form, except the d, the diffusion constant, will be different. So, what will it be? So, let us work it out. So, let us first of all just for a satisfaction, let us just draw the p, little p of x. X is discrete in this case. It could be 0, it could be 1. Can it be 2? No, because this is the elementary or the the possibilities at one instant. It can be 0 or 1 or minus 1. In fact, we have said that they are all equally probable. That is why I have drawn these of equal height. So, each has the probability 1/3, 1/3, 1/3, 1/3. So, first thing you are instructed to do is to calculate mu. Mu is the average value, but since this is a symmetric distribution, this is 0. So, mu is 0. What about sigma? Well, we go back to this. Average n squared is what we need. So, let us calculate it. So, there are 3 possible values of n, minus 1, 0 and 1, n squared times Pn. So, that is equal to 1 times 1 by 3 plus 0 times 1 by 3, I am summing over the 3 values, plus 1 by 1 by 3. So, that is 2 by 3 n squared. And so, sigma squared is in fact 2 by 3. So, that is the answer. So, it is a Gaussian. Is it narrower or broader than before? By before I mean that there was no weighting probability, you had a half and a half. Well, sigma squared is smaller now. Makes sense, diffusion constant will be smaller, because there is a chance it is not moving so much, it is just staying, it is not spreading that much, and this is the exact factor by which it is doing it. So, d is equal to half r. R is the rate which you are supposed to be given. A is the step length which is given, and sigma squared is 2/3. So this becomes 1/3 RA squared. So this is the ultimate answer in that problem. But it would be good if you work out the steps leading to this through the factorials. Okay, I am tempted to do another problem which is quite interesting and bears on this, and that is that you have two ordinary random walkers, usual random walkers, 1 minus 1, 1 minus 1. Okay, but now they have a certain, so one will have some location x1, one will have a location x2. Therefore, there is a separation. Suppose I do not care where is x1, where is x2, but I care about the separation. What will happen to the separation? How will it change in time? The walkers are, so by the way, there is a picture I should have drawn long ago. Let me do it. And that is, how does a random walk look in time? Okay, I mean time here and x here. Well, it goes this way, that way. You know, this is the typical trajectory of a random walk. Okay, so this is a single walker. Now along comes another one. That is fine. Here's two walkers. Have you all understood the problem? 1 and 2, each one is doing a random walk. Now let's look at the separation variable. Here's the separation. At this time there's a large separation. This time there's no separation. Here there's some separation. The separation itself is fluctuating. It can be positive or negative, because x, I mean if you define it that way, x2 minus x1 can be positive or negative. Can we work out what this separation variable is doing as a function of time? So let me just attempt it here. Each of them is doing an ordinary random walk, not a weighting random walk like this, but ordinary. So let's say we have, okay, let me use, this shows up better, at least it writes better, x2. Okay, x2 at the n plus 1 step. Okay, so what is a good way to write it? Can I just write it like this, n plus 1 is x2 at time n. Okay, what could it be? It could be this plus or minus 1, right? x1 likewise. Okay. Location of walker 2. And so on. So forget about x's, just look at the separation, x2 minus x1. In one time step, each walker will take one step, this way, this way, or that way, we don't know. But what can the separation do? Plus 2 minus 2. What about 0? Also 0. So is this clear? So I am going to the separation variable, name S y. Okay, y. Y. So y can be with something, but delta y, change in y in one step, can be 2. So let's write down the options at least, 2, 0 or minus 2. But there are 4 options. Where what happened? This could go right, this could have gone left. So this is happening with a larger probability, this one, than either of these. Because 1 could have gone right and 2 could have gone right, that's its probability 1/4. Or it could be that 1 went left and 2 went left, also probability 1/4. In both those cases, separation does not change. So the separation stays 0 with probability half. Is this clear, or shall I just do it in more detail right now? So, the probability of not moving, which was 1/3 in this problem, now becomes half. It will move 2 units to the right if the first walker moves right, right? Oh, sorry, what happened? Yeah, x2 moves right, but x1 moves left. Right, this has gone there and this has gone there. Separation has gone up by 2. But that happens with probability 1/4, because similarly the other one is also with probability 1/4. At least it's a good thing this adds up to 1. Okay. Is this much clear? We'll just draw out the events here. So, here is x2, here is x1. This could have gone right or left, this could have gone right or left. So, this happens with probability half, this happens with probability half, each of these. In order to increase by 2, this must have gone there and this must have gone there. That is the only way to increase. The probability of that happening is half multiplied by half, which is 1/4. On the other hand, it could be that this went right and this also went right. Or it could be, on the other hand, that this went left and that this went left. Probability of this happening and this happening was 1/4. Probability of this happening and that happening was 1/4. So, 1/4 plus 1/4 was half. Okay, good. But once you've done this bit of tabulation, you're through, because you have to do this calculation again, except you have to change your p of x, make this half and make this quarter and make this half. Okay, so 1/4, 1/2, 1/4. Mu is still 0. N squared is, can we work it out? What is the answer? Somebody can do it in the head. 2? I doubt it, but maybe you're right. Yeah, it's actually right, 2. Yeah. Remember, now these are steps of size 1. So, this is equal to, no. Oh, yeah, these are steps of size 2. Good point. Yeah. So, this is a step of size 2 in the separation variable. So, what happened? N squared will become 4 times 1/4 if we take this, 0 if we take this, and 4 times a quarter again. So, that is 1 plus 1 equal to 2. Very good. So, the diffusion constant will be half R A squared times sigma squared, which I think we have just worked out, which is 2. It is double the diffusion constant of any one walker. Remember this, the separation of 2 walkers grows broader. This is actually right, but see the amount of effort we had to put in, it was minuscule. I mean, we had to think through the options, but we have done it, and we are making a prediction for the asymptotic value of the separation. So, I am just trying to illustrate that you can attack a variety of problems this way. Yes, sir. A. What is A? Seems okay. No, did I do something wrong? It should be. No, 1 minute. The length of the step is 2a. Okay, did we do something wrong? This is okay.
Practice testing will remain the same. The same practice we are
Yeah, but yeah. So I think this is correct, but just to check, if you want to check, we'll put in a's everywhere. So instead of n, we'll put in average x squared, where x is the length of the step. Okay, what would happen? You'd put in a squared, n squared. You put in a squared multiplied by this 2a squared. Then I don't need this a squared there, but now we put it back. So it's a squared. Nothing happens, nothing else happens. This is correct. Just think it through in some other way if you want, but it's correct. Any other question? I'm moving ahead to point number 15. All right. So I'm rubbing these things out which refer to particular examples. We'll leave this here as it's a sort of nice picture and go to 15. Independent, what was it? IID, identical, identical independent normally it's that. So which I comes with? Independent
and identical.
Okay, independent and identically distributed variables. This is actually, I should have started by saying we have dealt with. We have dealt with. Can these be relaxed? The answer is yes, to some extent. Identicality can be relaxed so long as the probability distributions you are choosing your, you might be changing are such as to guarantee that so long as this sum over sigma I squared, so I'm just saying the average over average sigma squared is finite. This works, and independence is not guaranteed. I mean that you will get a central limit theorem, but it's okay if correlations are weak enough. Of course, I mean I'm not specifying how weak is weak and so on, but if there are weak correlations, it will still work. What is an example of a weak correlation in terms of random walks? Let me give you an example. I won't work it out, but let me just tell you. Suppose you have a random walk in which the direction of a step depends on the direction of the previous step. So, if it has gone right, it is more likely to go right than left, perhaps. So, example, random walker with step lengths sigma, I am using sigma of everything, that is bad. Okay, let me define a variable tau sub n equal to plus or minus 1. Tau n equal to plus 1 will mean right step, tau n equal to minus 1 will mean left step. Okay. The probability of taking a step tau n depends on the step at time n minus 1, which by the way is past. You are going from past to present to future. So, past is n minus 1, present is n, and we are saying suppose the probability that we have a given tau n, given this tau n minus 1. So, how shall I? Okay, so let me in fact write down a table that is more explicit. Probability that the step will be right given that the previous step was right is something. Probability that it was left given that the previous step was left is something. Probability that it is right given that it was left is something else. And okay. So, let us say that the probability that it is parallel, I mean parallel means sorry, it is continuing, is larger than 1, p, either this case or that case. For both, you can't have both together, by the way, because the previous step could be right or could have been left. So, in either case we say the probability is, well, p is perhaps bad, we are using p too much, u, and in this case it is v, where u plus v equals 1. What will happen to these world lines now? Well, so let us see, we start out maybe rightward, and then it is very likely that we will continue rightward. But having continued rightward, previous step is still right. So, we will probably go right and right again and maybe once again until by some chance, though v is smaller than u, it kicks in and then goes there. But the moment it goes left, it will not turn back right because now it is left. So, it will keep going left for quite a while. Until it turns again, but typically these stretches will be quite long, but it will turn. So, in this case, what do you think? Will the diffusion constant be larger or smaller? Larger. It will be larger, you are right, that intuition is right, because it is moving sort of ballistically for a while and then turning. It is as if you have an, a longer step length, roughly speaking, which depends on u and v. It is not exactly that. So, longer step length will translate into a larger diffusion constant. Okay. You can work this one out analytically, and I would assign it to all of you to think about how to do it. It is possible, and you should try to work it out. I mean, you will need some thinking on how to do it, but it is doable. I do not remember the answer, but it is not so hard. Okay. So, all right, so much about that. Number 16. Okay. Yeah, I was sort of reluctant to rub anything out, but maybe we will rub the homeworks out. What if the central limit theorem does not hold? So, these are all points we have addressed in the past, but I am just trying to do it in this sequence of things, so that you, in the sense that suppose sigma squared is infinite, what happens then? And what we said is that, for instance, typically if you have a power law decay of the variable p of x varies like this. Remember, power law decay is slow compared to Gaussian or compared to exponential even. If this is Gaussian and this is exponential, power law will be like that. I mean, okay, it may start lower just to conserve the area, but it will keep going. So, it turns out that in this case, there is this limiting law in terms of a new scaled variable, which is y x1 and since alpha we assume, okay, let us assume now if 0 less than alpha less than 1, suppose, then then this appropriate scaling of y is this way. Is it that way even for alpha between 1 and 2? It probably is. Okay. Okay. So, then this is there all the way up to 2. Okay. No, but what about the mean? No, I already have a 1 here, 1 plus alpha.
No, into the 1 by alpha.
Huh.
You take this one as square root of 1 when alpha is larger than 1.
Yeah, that is the thing. No, no, you don't take square root, but okay, just to be very sure, since this is a class, we'll put 1. It probably is true all the way up to 2, but we are not sure. Okay, so anyway, so 0, then in that case, in terms of the variable y, see here we did a separate scaling. We had a scaling with n which was root n. What is the scaling with n here? Suppose alpha is 1/4. N to the power 4 bigger than 1, n to the 4th. This is the most important thing you need to remember. Okay, and given all this, there is a function that results as a nice scaling limiting function. What happened to that ring? It just gave one ring and stopped. And nobody is talking. Okay, maybe it was an alarm, one shot alarm. Is it halfway? Ah, okay, good that it rang. Okay, okay. Yeah, I mean, these are the sounds of our times. You know, when you all have grandchildren, you can, you know, in our days, our mobiles would ring, they'll all laugh at you. What is a mobile? You know, right? You know, by then, you don't know what you'll be talking. You know, technology advances. Yeah. Okay, sorry about that, but so the typical way the Levy distribution of index alpha looks is very flat, increasing and then decreasing very, very slowly. Slow decay. I mean, nowadays nobody has genuine graph paper. They all have screens with grids on them. Take a graph paper, take a pencil and maybe a rubber and draw, put in these values and do it, you will see it's slow. You just see one line coming and you don't see anything. Do it. I mean, I don't know. Yeah. Everybody is looking very amused. I mean, okay. In fact, I've had a hard time buying an eraser. Nobody carries erasers anymore. Are erasers available in Belur? I will immediately buy 2. 17. No, I tried in Hyderabad before coming, but the store that I went to had CDs only, you know, and I don't know what are these things, pen drives. 17. Okay, so 17 and 18, let me just combine, and I just wanted to tell you in the context of all this, how would we use all this machinery or whatever you call it. It's actually not much machinery, it's mainly common sense translated into some mathematical form to characterize correlations. Okay. So, let me think of some system. I don't know whether to think of a magnetic system or let's think of a particle system. Except these particles are not on a continuum, they might be on a lattice. There may be electrons which are moving, from one side to the other, whatever. And let me look at least in this picture, but it could be any dimension, at one dimension. So, here we have a bunch of sites, and then we have particles which may or may not sit on a site, and in principle there could be more than one particle on a site, we do not mind, but let us say there is only one at the moment. So, it is either there or not there, it is an electron, spinless electron. That is what I am trying to explain. Yeah, okay. No, the way you should understand correlation is just the lack of independence. Any time that this probability distribution of some events happening cannot not be written as product, then you say you have correlations. Okay. So, you have usually you always have correlations. So, this why? Because usually dealing with Boltzmann weights or something, and they are all correlated. The particles are correlated, you can say, and that reflects itself in all properties, including joint probabilities. What is correlated? All the particles are correlated with each other, but if you try to describe all the particles together, you go dizzy. So, you do not try. So, you say let us describe two of them at least and see if they are correlated or not. But here we will not ask about two particles, we will ask about two sites. So, imagine these are your usual random walker sites, and you have a site I and a site J. In fact, we also addressed this a little bit when we talked about joint probabilities. Now, to find a joint, I want to know the following. Okay, so my rules are the following. Ni is an occupancy variable if site I is occupied. It is 0 if site I is unoccupied. So, if it is occupied, let me just fill it in. This is occupied, this is occupied, this is occupied, well, too much occupied. So, in this picture, site I is occupied, site J is not occupied. You could imagine other configurations. So, if you had a certain number of sites and a certain number of particles, you can count the number of ways you can distribute particles, etc., etc. But there could be energies associated with this. For instance, it could be a lower energy if two particles are close by, they are sitting in each other's potential well, in which case they get correlated. So, all right. Anyway, I just wanted to make a general statement about this. So, a good way to look for correlations, to hunt for correlations, almost foolproof, but actually not foolproof, is to but forget about the exceptions, is to look for the joint probability. Joint, you can write bracket, I won't write it, joint probability. Okay, so of an event. Event is that both particles have to be present, one at site I and one at some, well, let us make J quite far away, far off site J. I do not care what is happening in between, there might be particles, might be holes, might be anything. But if there is a particle here, is it sort of more likely than average that there is a particle there or not? This is the question. So, that is why I am looking at the event. So, yes.
Occupation of particle itself is event here.
No, not yet. I have not told you what the event is. So, the event is occupation. The event is that I must be occupied and J must be occupied. Both must be occupied. That is the event I want. Somebody else might want an event I is occupied J is unoccupied but K is occupied. Okay, you are welcome to your event. Anyone. Okay, my event is that I is occupied and J is occupied. That is the event I want. So if I have an event, what should I do? Hint, hint, hint. Indicator. Okay. So I need an indicator function to tell me I is occupied and J is occupied. Okay, can anybody suggest something? I into J? But I is like 25. I is a site. I mean, I and J are two sites, they are locations. Huh? So sorry, I should have said that. These are I and J are not particles. Huh? This is 1, 2, 3, 4, 5, 6, 7. My event is that on site 3 there is a particle, on site 7 there is a particle. We need an iter, but now, okay, forget about everything. What is an indicator function for site 3 is occupied? I mean, I want a function which is a variable or something which will be 1 if it is occupied, it will be 0 if it is not occupied. 2? Delta is there, but now in terms we already have something written on the board, can we use it?
Can I use the definition?
Yes, you can use any definition. Louder. Tau of yes. Yes. What you probably said is probably correct, but the simplest in our context is simply Ni multiplied by Nj. What is Ni? Ni is 1 if site I is occupied. Ni is 0 if site I is unoccupied. Similarly, Nj is 1 if site J is occupied, etc. So if I want the event I is occupied and J is occupied, I should just put in Ni Nj. Is this okay? Check, because if one is occupied, the others are unoccupied, you will get 0, which you should properly get 0, because you want only occupied. So probability that I and J are occupied, it's a joint probability, is equal to in probability of all options multiplied by the indicator function. Okay. So this is a sum over all configurations, probability of configuration C, okay, multiplied by the indicator function. But what is the indicator function? It's Ni in the configuration C and Nj in the configuration C. So this is by definition the average value of Ni Nj. Average value of Ni Nj by definition is called a correlation function. Well, okay, you may call this a correlation function or something else, but let us call this the correlation function. Let us call this Cij. So the answer to my initial question, what is the joint probability of occupancy of site I and site j? The answer is the correlation function Ni Nj. Many of you might have heard of a correlation function, then you just ignore it. Who cares? Yeah, it's the joint probability. It's quite, telling you something. Now, if it had been uncorrelated, then I claim it is clear that if uncorrelated, then you will agree or perhaps not agree, I do not know, but it is true that this will factorize into average Ni times average Nj. It is saying that the joint probability of occupancy of I and j, well, in order to occupy I and j, you occupy I probability and average Ni, occupy j probability, multiply the two. But you can multiply the two if they are independent, if they are uncorrelated. So, if they are uncorrelated, this is true. So, because of that, one often also defines a function Gij equal to average Ni Nj minus average Ni Nj. It is the difference of the joint probability of occupancy from what would have happened if the variables were uncorrelated. So, it tells you something about the correlation. If Gij is 0, uncorrelated. If Gij is not 0, correlated. If Gij is positive, it says if there is a particle here, it is more than usually likely that there is a particle there at J. If Gij is negative, can happen, does happen, it happens in liquids and in all sorts of things. So, depending on the separation, Gij can be positive or negative. I mean, nothing can stop that. Negative has a simple meaning. If there is a particle there, it is less than usually likely that there will be a particle close by. Okay. So, this has a lot of physical, what is the word, meaning to it, correlation. You know, the word is something that we understand, something if we want to quantify, this is a good way to do it. Okay.
Either of those lattice points are not occupied. I am going to make correlation 0.
Correct, Cij will be 0. That is right. That is because I have demanded the event. My definition of event is, you know, this one. I want both to be there.
Not necessarily both. If one is not occupied, it is not correlated.
Okay, can you repeat?
No, I understand the question. They are said to be non-correlated if both sides are empty.
No, I mean both. Yeah. I think everybody will agree that it could be that both sides are empty, or it could be that one is empty and one is full. All will be not contributing to the event. Both sides are full. That's all. It's not a very, what should I say, profound statement, but it's a useful way to think about it. So, please remember always to look for correlation functions, whatever you do. If you are studying liquids, look for correlation functions. If you are studying magnets, look more for correlation functions. If you are studying ferroelectrics, look for correlation functions. It turns out correlation functions are very easy to measure. You might, as a function of the separation. That is perhaps not obvious immediately, but these are measured by scattering experiments. In magnetic systems, it will be neutron scattering. Why? Because, you know, in some sense, if in a magnetic system, the corresponding question would be not occupied. I mean, there are spins everywhere, but are there spins parallel? If there is an upspin here, is there an upspin there? You know, so we want the probability of that. So, you know, you can imagine it roughly this way. I don't know whether it will work. Well, no, I mean, the point is that a neutron coming in, by the way, you know that a neutron is charged how much? 0. Magnetic moment, yes or no? Yes, yes, yes. So, neutron is an ideal particle to measure magnetic properties. It's not influenced by charge and so on. So, it comes in and it sort of senses this spin through some interaction with its own moment. Now, the neutron also has a certain wave vector, and if the other one is sort of within that wave vector, I mean, well, not it could be further away, but okay. In some sense, it carries some information about this first spin as it goes away. In fact, the neutron might have been a down spin, and maybe this spin made it up, through some interaction. There are appropriate Kondo, whatever interactions. You go ahead, and then this information is again transmitted. Somehow the neutron is able to sense that, and as it scatters and goes away with some momentum k, which you measure, this cross section of scattering will depend on how parallel or not parallel spins were at different separations. That k you can translate back into r. It's Fourier transform. K meaning wave vector back to real space, and you can get beautiful and very accurate plot of correlation functions, how these functions decay as a function of r. So, never mind the actual measurement process, I haven't described it very accurately, but the fact is that, okay, let me give you another very simple, in fact, I don't know whether you all would like to, but this is an experiment that can be set up. By the way, we have been lazy in TIFR Hyderabad, we have not done it yet. I have done it in the past in TIFR Bombay, and that is the following. This extent of, so correlations of course happen. It's a fact of life. Things are correlated more than not. I mean, but correlations do decay in space usually. Simply it's again in the nature of randomness and noise and temperature and other things to destroy the propagation of information, information being that this is a spin up, how far will it be felt, or here's a density fluctuation, how far will the liquid sense it. However, the length over which this decays varies hugely within a few degrees Kelvin if you are close to a critical point. Okay. So, for instance, if you take a binary liquid, which is the canonical example? Cyclohexane and methanol. So, this is a good example to actually try to work out a demonstration in class also. The point is binary liquids mix above a certain critical temperature, and then they separate and give you a meniscus between them below a certain temperature. That temperature at which they just mix is called the critical temperature, cyclohexane and methanol in the right proportion, which can be found, but okay. Now, I claimed that okay, I think we can say. So, as I said, if you have cyclohexane and methanol above Tc, it looks like this. Cyclohexane, methanol below Tc looks like that. One is cyclohexane rich phase, one is the methanol rich phase. This is a test tube. But what is happening is that you have some macroscopic separation of something. So, at Tc, what is the manifestation of this? It's neither this nor this, but basically what you form is big droplets in some, they are not actually macroscopically sized, I am just drawing them. So, if you magnify this, there is a droplet, and there's something inside that. This is C rich, this is M rich, this is inside the M rich thing you have another C. So it's a very finely fractally composed mixture. It's a critical point. It's a very, very special point. It doesn't matter, by the way, which liquid you're using. The same thing will happen and with the same phenomena in all liquid mix. But okay. Now, so basically what is happening is that, remember, you're getting big sort of chunks of density fluctuations. C rich, M rich, C rich. This was at the atomic scale that they were mixed. Now you have to reach a situation below TC where they are actually separated. So at TC you have all length scales of these fluctuations. So what happens is quite striking, because if you are looking at this, what does it mean that you look? To look, you are looking and seeing. So to see something, there has to be some light coming through. Okay, so if you just put this against a bit of light, when you look through, this is totally transparent. Okay, when you look at, finally here also it's transparent, both. But over here, it becomes totally milky. Now, what is the implication? Milky means light has scattered. Would you agree? What is the wavelength of light? What are the units? Angstroms. Okay. All right. Okay. Nanometers. Okay. Fine. 600 nanometers, let's say. 600 nano. Let's deal with nanometers. Everybody is talking nanometers. Only some 4 people in front are familiar with angstroms. Okay. 600 nanometers. But what is the interatomic spacing? 0.1 nanometer. 0.1, 10 what? 10 angstrom is too big. No, 2 angstrom is more like it. Interparticle spacing. 2, okay, we'll round off 2 to 1. Okay, so 1 and here 600. In order for something to scatter light, it has to be of the order of 600. That means this correlation length, the length over which the correlations decay, has grown to 600 times what it was. So if I plot, here is TC, here is the correlation length. I haven't defined it, but here it is. Here's the definition. G of R falls as e to the minus r over xi divided by r to some power, but okay, xi. This xi actually is becoming 600 times by the time you change the temperature by 2 or 3 degrees. So it's a dramatic rise, equally dramatic fall. So this is the way it behaves, and you can see it. So what I'm trying to tell you all is that correlations are very, they're sensitive to many things, including the temperature and the closeness to the critical temperature, and this is the way they behave. Somewhere along this, if this is 1, I suppose 600 will be higher, but let's put it here. Oh, is it? Okay, good. Nobody corrected me, but I'm glad you did. Okay, but now we'll put in that 2. So divide by 2. Now we are willing to do it. So it's 3000. Okay, give or take 1,000. Yes, make it 2,000. All right. I'm in a very generous mood. So 2,000 times. I mean, within 3 degrees. I mean, what is happening is the system is approaching a critical point. Actually, at the critical point, many other things happen. They're actually miraculous. We will not get into that. But what I wanted to show you is that correlation functions which are joint probabilities which go back to indicator functions, and these ideas actually tell you something rather physical and dramatic that can happen. And on that happy note, I'll stop. Thank you. I don't know, there were other stuff, there's other stuff, but this seems like an appropriate time to stop. Okay, by the way, I will be continuing.